Welcome to one more coding challenge about trees. And in this coding challenge, I'm going to use an algorithm called space colonization, which does not have to do with colonizing space, although that would be interesting. It's really about colonizing a two-dimensional space of leaves in the screen. And you'll see how that makes sense as soon as I start to diagram this out. So first I want to mention this algorithm is from a 2007 paper that you can read on algorithmicbotany.org. I'll include a link in this video's description. There is also a tutorial that I used in preparation for this from the Sea of Means website. And I will also, which goes through this space colonization algorithm, and I'll also include a link to this particular tutorial as well. So I'm going to do it in this video simply in 2 dimensions in JavaScript. That's a processing version that I already made earlier this morning. I'm going to program it again from scratch in JavaScript. And then in a separate video, I'm going to extend the concepts into 3D to see if we can create a tree in 3 dimensions. So first, before I start programming it, let's just talk about what this algorithm is in a very general way. So most of the fractal tree type algorithms that I've done in previous videos or that you may have seen work with this sort of methodology of always growing from the bottom. A branch grows from the bottom and it branches and it branches and it branches, and et cetera, et cetera, et cetera. We saw an L system is a very similar thing about starting from a point and following these drawing instructions to kind of spread yourself out around the screen. The way the space colonization works is, let's say this is your canvas, and you have some volume, some little area, and you can imagine like creating something sort of tree-like like this that is filled with leaves. And the leaves are represented as dots. So in other words, in a way, instead of growing from the bottom and reaching the end, this algorithm starts with the end. Like just a random sea of dots, those are all the leaves. Then what happens is you create these segments, and each segment is attached to another segment. And once a segment starts to get close to leaves, it becomes attracted, almost like gravitational attraction to those leaves. And when it gets attracted to a leaf, it spawns another branch, which then, as it goes more forward, or segment, which as it goes more forward, might start to get attracted to another branch. So, this is sort of the basic idea. And as I start to write the code and get the code for the branches, the segments, the branch segments, and the tree and the leaves going, we'll start to see a little more of the nitty-gritty of how this algorithm really works, and I'll come back to this diagram. So let's come back over here, and I'm going to go to the browser. This is what I have so far. It's a blank canvas, and I'm going to go to my code. And all I have right now is setup and draw. But I've already created, by the way, a whole set of other JavaScript files that are empty. But I know I want to have a leaf object, I want to have a branch object, and I want to have a tree object. So the first thing I'm going to do is write a constructor function for a tree. And in that tree, I'm going to have an array of leaves. And when you first make a tree, I want to create, and let's just start with 100 leaves. So I need some way of creating all the leaves at first. So I'm going to say this.leaves.push a new leaf. So the very first thing I need to do is just create all of those leaves that are going to be in the canvas. So I've got that. And now, in leaf, I now want to write a function for a leaf. And a leaf is just something with a position. So this.position equals create vector. And what I'm going to do actually for simplicity is just make a random location in the canvas. So the very first thing I do is I just create a leaf object that has a position vector. And the tree object makes an array of 100 of those leaves. And I could also have a function here like this.show. And I could say for all of the leaves, have each leaves index I. So to draw the tree, draw all the leaves. Okay, so that means now I have to go to the leaf and write a show function. And in this show function, I'm just going to draw the leaf as a circle at this.pos.x, this.pos.y, and 4 by 4, and maybe the leaf here for simplicity is white and it has no stroke. So if I run this particular sketch now, I still see nothing. Why do I see nothing? Because what I need to do in my main program is I need to say I'm going to actually have a tree, and I'm going to make, in setup, I'm going to make a new tree, and then I'm going to say tree.show. Okay, leaves is not defined, tree.js.10, and this is what I've forgotten, is this dot length and this dot leaves show. Okay, so you can see this is how I could start. I could start with just random leaves. Now, how the tree is actually going to look, where you place those leaves randomly can really make a difference. Are they within a box? Are they within a circle? Or within kind of like a heart shape? So there's a lot of possibilities there, but this is kind of the basic idea. And we could see what happens if I create 500 of them. Now there's many more leaves in the window. So now what I need to do next is create a branch, the root of the tree. So I need to figure out what goes in these branch objects. So the branch objects, have I been in the wrong place the whole time? No. The branch objects are these little segments. And the way that this is going to work, here's an implementation that you could do, is you could create a branch object really just only as a position. And then when you make a new branch object, that new branch object also has a position, but it also stores a reference to its parent. And if it knows a reference to its parent, that segment can always be drawn as a line between its parent and itself. So each segment is really just also going to be a dot. So we're going to start with that. So what I'm going to do is I'm going to create a branch object. And the branch object is also going to have a position, and it's going to have a parent. So its parent is another branch. So its position is probably something that I'm going to want to get, maybe as an x and a y, or even better yet, as a position. And its parent I also want to get as a parent. So look at this. So I want to create, whenever I create a branch, I want to give it a position and the parent it's connected to. Okay, so now if I go back to tree, in addition to creating a bunch of leaves, what I want to also create is the root of the tree. So the root of the tree is a new branch. And where should it start? It can really start anywhere. I'm going to weirdly start it in the middle of the window. I think that might be interesting. And so I need a vector. So I'm going to say var position equals create vector in the middle of the canvas, width divided by 2, height divided by 2. And I'm going to make a branch at that position. And the root of the tree, what's its parent? It has no parent. So I'm going to just say null. So the root is a kind of special case in which that it has no parent. So I'm going to have that root. And then I also want to have an array of branches. And I want to take that root and add it to that array of branches. Okay, now, the question, and you know what? I totally forgot something really important. So by definition, the way that this attraction algorithm is going to work, imagine there are like 3 leaves here and I have a branch here. The branch, by definition, needs to have a direction that it's pointing. Because the next branch is, and really I should use the word segment, the next segment is going to be added at the end, and it's going to get a copy of its direction, but it's going to get pulled toward the closest leaf, which is what's going to cause this kind of meandering of all of these segments. So what I need to do in addition is give, where am I? I need to be in branch. Each branch needs to have a direction. So the direction is also something that I can get from the constructor. And so when I make that root, I need to, and where do I do that in tree? I need to also give it a direction. So I think the order of my arguments here is a little bit weird. I make a new branch, add a position, and then, and null is the parent. Let's go look at that again, sorry. So position parent, let's put the parent first. So I'm going to, let me come back here. And I'm going to say, sorry, tree branch. I lost this. Where am I? Tree. I'm going to say position. Null is the parent. That's the position. And now I also need to give it a direction. And I'm just going to arbitrarily have it pointing up. So this would make sense, especially if I have a root of a tree like pointing up. So I want to have that tree pointing up. So one thing that I need to do is, here's a key. There's a key set of, there's a key piece of data in this algorithm. There's a lot of pieces to this algorithm. But key piece of data are something called a minimum distance and a maximum distance. And if you read the paper, this will be described in the paper. The idea here is that later you're going to see that I'm going to be looking at the leaves. And I'm going to look at the leaves, a leaf's distance to various branches, various segments that are in the system. And the leaf, for it to be relevant, has to be between that minimum and maximum distance. If it's too far away from any branches, it doesn't play a role. If it's too close to a branch, it's actually been reached and it's done. So one thing that I need to do when I start, if I only have this single branch, I need to make sure that branch is at least within a maximum distance of one of the leaves. So the first thing I want to do is add this maximum distance variable. And I'm just going to say like a big number for now and a minimum distance and a kind of a small number for now. So I'm going to say 510 is kind of arbitrary numbers that I'm going to pick. What you choose for these values can really affect the system. And then what I'm going to do in this tree constructor is I'm going to say, OK, I made this root. And what I want to check is what is the distance. Oh boy, there's a lot going on here. P5 vector dot distance between the root's position and any given leaf. OK, so I need to loop through all of the leaves. OK, I need to loop through all of the leaves. Leaves index I dot pos. So I need to check the distance between the root's position and the leaves position. And if the distance is less than max distance, then we've got a branch that's close enough to start doing the algorithm. So I want to say var found equals false. And then I'm going to say found equals true. And actually what I want to say here is current equals root. Because what I'm going to do is I'm going to say while not found, keep doing this. So what I'm going to do here is I'm going to say I want to like check this beginning root. Like the tree's going to keep growing just in a straight direction until it's close to some of those leaves. And this you'll actually see in most cases. We'll do this later. All the leaves are at the top and the root starts from the bottom. So it's just growing straight up until it reaches the leaves and starts to fan out. So I start by assuming it's not close enough. But if the distance is less than max distance, found is true, and this while loop should stop. But if it is not found, then I need to make a new branch. And how do I make the new branch? I can actually take that root branch, right? Remember, a branch, this is tricky. A branch is a position and a direction. So what I want to do is get a next branch, a next segment attached to it, which would be this new position and a copy of that direction. So what I can do is var branch equals, and what I want to say is current.next. So why not just have the branch itself give me the branch that's attached to it? So if I go to the branch, I could write a function. And this is kind of recursion here in a way. Next is a function where, what does it need to do? It needs to make a new branch. Next branch is a new new branch. And where is that new branch? So first of all, the next branch is its parent is this particular object. That's its parent. Its position is this particular branch's position plus its direction. So I need next position equals add this position and this direction. So next position, and then its direction is just also this branch's direction. But I want to be careful about this, and so I'm going to call the copy function, because I want to make a copy of the vector in case various branches change their direction. The original one should keep their original direction. So then I can say return next branch. So what am I doing here? If I go back to the tree, what I'm doing is I'm getting the next branch, and then current equals, current now equals that next branch. And I also want to say branches.push current. So this is what I'm going to do. Now, I'm not sure I 100% got this right, so I need a way of testing this. So first of all, let's just run this. So branches is not defined, so I have some errors. So I guess I decided I was going to, okay, so I can never remember to say this. So anytime I refer to branches, I need to say this. Leaves is not defined in line 20, so I need to say this dot leave and this dot leave. And cannot read pause of undefined in line 21. Whoops, back. I had forgot a little bit of code in the for loop there. So let's take a run this again. Okay, so I don't see anything here because I'm not actually drawing those branches. So let's go through now and say also for var I equals 0, I is less than this dot branches dot length, I plus plus. And what I want to do is say this dot branches index I dot show. So I want to draw all the branches. So I need to go to the branch object, and I also need to add a this dot show function. And now, as long as parent is not equal to null, so remember, this is only the root doesn't have a parent. What I want to draw is a line from this dot position dot x, this dot position dot y, to this dot parent dot position dot x, this dot parent dot position dot y. So let's make this line white, and so now if I run this again, let's see here. Now let's change this around a little bit. What I want to do is actually have the tree start, the root start from the bottom, and let's actually also have the leaves get a random location that's about 100 pixels off of the bottom. So in this case, we should see the branches being attached to themselves up until they get within maximum distance. So, although maybe the first one is my maximum distance is so high. Yeah, so that worked. So you can see here now, this root is going to go all the way up until it gets within a certain number of pixels of one of those branches. Okay, so now once that's done, that's the thing. So let's just review what we've got so far. The only thing we've done so far, let me come back to this diagram, is start with, and I'm going to draw this again over to the right. We've started with segments that are approaching the leaves, and once one of the segments gets within minimum and maximum distance, we need to do something different. Okay? Then we stop. So we're really just working on getting the root of the tree in place. And once we get the root of the tree in place, this is where things start to shift. Instead of working from the branches, we're actually going to work from the leaves. Okay, so let me come back over here. And now what I want to do in the tree, so this is all the stuff that's kind of happening just at the beginning, just to get the tree sort of set up. And now what I want to do is add a function called grow. And in the function called grow, I want to look at all of the leaves. So we're going to go through every single leaf. Var I equals 0, I is less than this dot leaves dot length, I plus plus. And I want to look at each leaf. So each leaf is this dot leaves index I. For every leaf, what I want to do is figure out what is its closest branch. Does it have a closest branch that's in between the minimum and maximum distance? So here, what I need to do is say var j equals 0. J is less than all of the branches dot length, and it's this dot branches, j plus plus. And before I do this, I need to figure out a couple things. I need to, what I'm looking for is the closest branch. I'm going to assume that to start that there's no closest branch. And I also might need the closest direction. So the direction of the closest branch, but that's in the branch. I don't need to worry about that right now. So I'm going to look at every single branch. Okay, so the main thing I need to do is look for the distance. This is really hard. This is very long. I don't know if this was such a good idea, this particular algorithm. Should have done this in multi-parts. Whatever, this is how it's going today. Okay, so what I need to do now, I'm looking for the closest branch. So I have to find the distance, right? The P5 vector distance function gives me the distance between two vectors. So I want the distance between the leaf's position, and I'm also going to just make a separate variable called branch, which is this dot branches index j, and that branch's position. So a couple things. If that distance is less than minimum distance, so leaves only exist to attract branches toward them. Once a branch has reached a leaf, that leaf is no longer in play. So we have to mark that leaf for deletion. So I'm going to say leaf, it's reached. Leaf.reached equals true. So that means I need to go back to the leaf object and add a variable called reached, which is false. And we'll use that for something later. So the main thing I need to do here in this particular tree, in this particular part again, okay, I'm looking for the closest branch. But if I happen to find a branch that's too close, I'm done. Leaf is reached, break. And I think I might have, when I was doing this earlier, I think this might be an indication of the bug. There was a bug in my code previously, and I think maybe this is where it was. But we'll find out. Now, otherwise, else if distance is greater than max distance, then also forget about it. This is something to be ignored. If it's still greater than max distance, forget about it. This particular branch should be ignored. Actually, no. I shouldn't break because I want to check other branches. So I don't need to break. I just don't want to include it as anything relevant. Else if closest branch is null. So if it's not too far away and there is no closest branch yet, guess what? It's the closest branch. So that means closest branch equals this particular branch. And what do I need? I need a record, right? That record distance, because I want to know if I find another branch that's closer, is it even closer? So I'll make up some really big number to start with. That's kind of ridiculous. That's plenty big. And then the record is that distance. Now, otherwise, last thing, else if distance is less than that record, right? If closest branch is not null and it's not greater than the maximum distance, if distance is less than that record, then guess what? We have a new record and a new closest branch. So you can notice here that I'm doing the same thing, right? If it finds something that's null and it's not greater than the maximum distance, there we go. I really think that was the problem in my previous code. And then otherwise, so both are the same thing, so I can actually put an or here. If you notice, like if ever like these two elses do exactly the same thing, if it's null or if it's less than record, then then this I can shorten this. So I'm going to do this. Okay. So here we go. So this is this whole entire algorithm. For every single leaf, I'm looking for the branch that's closest to it. And it has to be between the minimum distance and the maximum distance. So the question now becomes, for every leaf, after we've looked through all of the branches, what do we do? What do we do if closest branch is not null? That means we found something. That means what we need to do is make a new branch with a new direction. Time out, pause. Back from a momentary pause, I realize there's a very big crucial error in here. The thing that I'm checking, right, I'm trying to find the closest branch. And the way that I know I haven't found a closest branch yet is if closest branch is null. So this should not be checking if it's not equal to null. This should be checking if it's equal to null. And I could use 3 equals or 2 equals. It's a little bit interchangeable in this spot. Down here, later, I'm going to check, did I actually find a closest branch? So now I have this segmented out. If this particular leaf is so close to a branch, the leaf is done, and also this, I can also just be safe about this and set closest branch equal to null. If it's greater than maximum distance, do nothing. And if it's in between minimum distance and maximum distance, then is it actually the record at this point? If it's the first one, it is the record, or if its distance beats the record, it is the record. Okay, once we have that, we now have our closest branch. So when we have the closest branch, we need to do something. We need to create a new branch or a new segment. And let's look at how that works. So here, I have an existing branch, this particular branch. And this is an existing leaf. And this leaf is the one that's determined to be this branch is closest to this leaf. What I need to do is get this as a direction vector, normalize it, right? I want it to be of length 1. Okay, well, hold on. Let's not worry about the normalizing it for a second. I need to get this as a direction vector. Essentially, I want to add a new segment, but I want this leaf to essentially attract it. I want it as if this leaf is pulling on the next segment. So instead of the next segment just going straight up, it goes this way. It doesn't go directly to it. This is like a force that's pulling it in that direction. Because here, if this continues, the next segment is going to pull even more. And eventually it's going to get so close that this leaf will then get deleted. So that's why I'm going to get these nice curvy, veiny looking paths. So how do I pull it? A way of pulling it is normalizing it and then adding it to this particular direction and then putting that at the end here. So let's look at how I might do that. So here with closest branch, what I need to do is create a new direction, which is subtracting. What am I subtracting? I'm subtracting that particular leaf, right? I'm on a particular leaf. That particular leaf's position minus the closest branch's position. And then I'm going to normalize it to make it of length 1, just as sort of a generic, and I could scale it in different ways. You could try different things to play with it, but I'm going to normalize it to make it length 1. And then what I'm going to do is create a new branch. Pause. Back again after an edit point. I did have a problem here. This, by the way, closest branch, I meant to set that to null, right? Not true. The point is, if it's within that minimum distance, it doesn't count. Set closest branch to null. Now down here, what I need to do again, I'm back here, I'm back thinking of this, I needed this branch's direction to get pulled towards this particular leaf. So what I want to do is say, take that closest branch, and then I want to take its direction and add this new direction. So I used the direction variable way too many times. So I'm going to call this new direction, just to be less confusing. And I'm taking that existing branch. I found the branch closest to that leaf. I got the direction. I found the branch closest to that leaf. I found its direction. I found that direction, and I'm moving its direction toward that. And the other thing I need to do is the branch then, part of this algorithm is actually having the branches have a count variable. So the branch needs to count how many times it's been found near one of the particular leaves. And we're going to see this later because this is going to be important because I want to average all of those sort of forces together. So what I'm going to do here, so I add a count variable, and then I say closest branch dot count plus plus. Okay? So let me recap that. This is pretty confusing and tricky to see if I can make this make sense. I have a branch which has a position and it has a direction. And I have a bunch of leaves. So let's say if I'm going to show you these two leaves. So this leaf finds itself closest to this particular branch. So what I do is I make a vector that points from here to there. I shrink it down and I add it to the direction. So now this branch's direction is kind of going like this. Now later I might find this particular leaf is also close. So I need this particular vector and I add it to that. It comes back over here. So these as I go through all the leaves, I'm pulling various branches, segments that might be close and stretching them. So not stretching them is the wrong word. The pen cap went, but pulling them as if it's a force. Okay, so this is now done, right? This part of the algorithm is done. I'm looking at every single leaf. The leaf, if it's less than minimum distance from a branch, for every leaf I look at every single branch. If it's too close to a branch, we're done with that leaf. If it's too far away from the branch, that branch is not a candidate. If it actually is the closest one, I'm going to keep track of it, and that branch is going to be attracted to that particular leaf. So once I've done that, now it's our job to do the following. The first is I need to go through and find any leaves that were too close and delete them. So I'm going to loop through, and I'm going to loop through the leaf array backwards. Because deleting things from an array, you need to loop through it backwards because you're taking stuff off the end so as to not mess it up. So I starts at the end of the array, goes down to 0, and then I minus minus. So, and I'm going to say if this dot leaves index I was reached. Remember, I have in the leaf object, I have a reached variable that's set to false. And what do I do in the tree? If it's within the minimum distance, I set that reach to true. So then later I can go through in a separate loop. I could have done it in the loop above, but just for simplicity, I'm doing this in a separate loop. I can then say this dot leaves splice, delete one element from the array at index I. So that's the first thing I can take care of. The next thing I can take care of is I need to go through all of the given branches. So now I need to look at every single branch. And I need to figure out what branches were attracted to what leaves. So how do I know if a branch was attracted to a leaf? Well, I know if its count was increased by at least 1. So branches could be attracted to leaves 0, 1, or more times. And I only care, and I'm going to say var branch equals this dot branches index I, just to make my code a little easier to work with. I only care about branches whose count is greater than 0. And if their count is greater than 0, what I need to do is make a new branch attached to it. So how do I do that? So the first thing I need to do is I need to actually average, I need to divide by count because I was adding all those vectors to it. And if it was near 10 different leaves, then I want to divide by 10. So what I should do is take that branch's direction and divide it by that branch's count. So that's a way of averaging however many branches I was sort of attracted with a force. And then I want to make a new branch. So if I make a new branch, I always need 3 things. I need the branch's parent. The new branch's parent is that existing branch. Then I need the branch's position, which is that branch's, the parent's position plus that branch's direction. So new position equals create equals add add the previous branch's position with that branch's direction, and that's the new position, and then also the direction. And I'm going to copy it. Now, I have some redundancy here, because honestly, if I could actually write a function in the branch object to produce the next branch, and I did that actually in a previous processing version of this that I did. But right now, this is where we can see what's going on here. I have to make a new branch, right? This is a branch that's growing. Its parent is the previous one. It gets a new position based on that new direction, and also it's got to store that direction in case it connects to it starts being pulled towards leaves as well. And then I should just be able to say branches. This.branches.push new branch. Well, someone's telling me line 66 I forgot to add. Thank you. So this should add those two. Thank you very much. Okay, so let's, I think that's kind of everything. This is the grow, this is the grow function. Let's just run this and see if I have any syntax errors. So this still looks about right. But I didn't actually call the grow function. I'm a little bit afraid to. I added a ton of code. But I'm going to add that grow function now in draw. I don't see anything happening. Okay, so we got to figure out what am I missing here. At least I'm not getting any syntax errors. Let's first at least see if grow there might be getting stuck in an infinite loop somewhere. So in the tree function, I'm going to just console log growing. So let me just make sure this is getting called over and over again. Okay, so I'm not stuck. Things are looping. Oh, the count has to be reset. So I forgot something very important. Each generation, I've got to reset the count, and also actually the branch should have its original direction. It shouldn't change. So this is great. I forgot an important step. No wonder I don't know if this is what's causing the problem, but I certainly didn't forget a really important step. So branches have to be reset. So one thing I want to do is say original direction equals, so I always want to keep a copy of the branch's original direction, because after a branch's direction gets manipulated in order to create the direction of the next branch, I knew I forgot something. I need its direction to go back. And I need to copy it again. So I need to restore its direction. I could probably, after I do this, I could probably go through the code and find extra places where I copied vectors. But I have to be very careful that I don't by accident have vectors pointing to the same data, changing it one place, it changes it to another place. And I also need to reset count by 0. So what I need to do is at the very end here, when I go through all of the branches, I need to once again, and I should go through the branches. This is bad, by the way. I'm surprised that this didn't cause a major problem, because I'm going through this array of branches and adding to the end. So here I also want to start at the end of the array and go backwards down to 0, and then add to the end. And I can also, just for safety, I can reset all of the branches. So this is definitely something that I missed. What I need to do is, as I'm going through the branches for the ones that were close to leaves, to create the next branch, I create the next branch and then reset that branch. And so now, okay, original dir is not defined. Where's that in branch.js line 9 of so this, by the way, needs to say this.dir. Actually, it kind of worked because that's there. And then this also needs to say this.original. Okay, so promising. This is all still growing. So what did I miss? Okay, so let me look here in tree and see where things might have gone wrong. So let's just see, is this actually happening? Am I finding things? I'm not finding any closest branches. Now, I wonder if there's an issue with my just my like, oh, maximum distance being the same as minimum distance. That can't be good. How did I do that by accident? There we go. Something crazy is happening. Okay, so that kind of worked. I think maybe my distance was too short. Something, oh, this is kind of doing stuff now. Hey, I like how this works. Okay, it's working now. We're getting a nice little tree growing and branches being attracted to leaves and things being spread out. You can see how it's working. I think this is kind of about right. So there's a couple things that I'm noticing. It's actually running quite slow. And something I could do to kind of speed things along that makes more sense is also to have the branches have kind of a minimum length. The length is based on the direction vector, which I didn't actually normalize. I just realized, I think there's some technically some correct way of doing this that I probably missed. So if I go here, when I made the new direction, let me find that. Where is that? Oh, I already had this next function. Look at that. I forgot that I had the next function. So this is actually, could be, one thing I could do to improve this, I got this now. Sorry, back, where is that? In the tree. I don't actually need to do this here. I should be able to just say, this dot branches dot push new branch dot next. So I should be able to use the next function, which just gives me that next branch based on that. So that I should be able to use. This should be identical. So that saves me. I have that next function. I should use that. And the reason why I thought back to use that is because I should just do this entire video again because I understand this algorithm so much more now from having to be in this very awkward place of programming it live. But what I want to do here is go back to that next function, and what I can actually do is I can say I'm going to make I'm going to multiply this dot direction times 5. Right? So this is kind of like the length. I can actually give this a length. So branches can have a sort of default length, and then I can add that. So if I do that, I know I did that kind of quickly, but what you'll see here is it's kind of growing much faster now because each branch by definition moves by 5. And I wonder if actually this should always be normalized. I don't know if that really makes a difference. I think it's the same. I think by definition, because I divided by count, it might have been, that's sort of like normalizing it. But anyway. So this is pretty good. So I'm going to stop here because I'm going to do some, I'm going to go back to this algorithm and look at it in 3D and maybe, but here's the thing. So I'm going to post this code. It'll be linked in the description of this particular incredibly long video. I don't know, it's 45 minutes long. But really what I want you, if you've watched this, if you've stayed with this, if you're working with this code, somebody in the chat, Oliver in the chat, has made an excellent point, which I'm going to fix before I go on. But what I want you to do is think about how are you arranging those seed leaves? What is your minimum distance? What is your maximum distance? What is your length of each branch? So what types of patterns, leaf, veiny, tree-like patterns, even in 2D, how can you use color? How can you use thickness? The more branches that are layered in the same spot, can you make it thicker? Try some of these ideas, improve on this, and I'll try to come back in another video and kind of make these improvements because I think it would be good to do a follow-up on this. But let me just fix one thing. I don't need to normalize the direction because I divided by count. But where did I divide by count? I divided by count here, but I really should be dividing by count plus 1 because I'm also including the original direction vector, which is a unit vector. So I've added that unit vector with all the other unit vectors of close leaves, and so there's one more there. So that should probably make things more quote unquote correct. And you can see how this works. So I'm just sort of curious just to play with this for a minute here. Like for example, in tree, what if I give myself only 50 leaves? You can see kind of what I get there with only 50 leaves. What if I give myself 1,500 leaves? You can see what's happening with 1,500 leaves, and you can see some are getting kind of like, some of these like perfectly equidistant ones are getting ignored, like the branches just go right through the middle of them, which is kind of interesting. But really what would be more interesting would be for me to arrange the beginning. Okay, I have to end this video now. I'm going to move over to processing in the next video and look at this same algorithm and try to extend it into 3D. And at some point I might come back and try to do that in JavaScript in 3D as well. Okay, thanks for watching.